Continuing on physical chemistry, we're in chapter 15 doing section 3 now. In this section we're going to talk a little about temperature. So let's say that we have two substances. We have a liquid, it's a temperature we'll call T1. And we have another liquid, we'll call it liquid 2, and it's a temperature T2. And these liquids are in contact. What we can say is that thermal energy will flow from hot to cold until they have the same temperature, which we said before is our definition of thermal equilibrium. So one thing we do know, at thermal equilibrium, T1 is going to be equal to T2. Now another thing we also know is that the average energy of translation of liquid 1 is going to be equal to the average energy of translation of liquid 2 at thermal equilibrium. So we're going to say that T is some function of the average energy of translation. Now this function, of course, depends on whatever temperature scale you want to use, such as Fahrenheit, Celsius, Kelvins, etc. Now, if temperature is constant, then the average energy of translation is constant, and therefore the average energy is going to be constant. Remember, lowercase, this epsilon we said is for per atom, and this capital E we said is for the whole aggregate. So PV is going to be constant at constant temperature. Now we showed before, previous section, that PV is, remember this is pressure times volume, is equal to 2/3 times the total energy of translation. So energy in translation is the total average translation of energy, I should say. So you get an average energy for each molecule and then add them all up. It's a sum or integral. So 2/3 times the energy of translation is constant as long as you have constant temperature. Now let's say that we have this number K, a constant, that's equal to 2/3 energy of translation. Then we'll say PV is equal to K as long as you're constant T. That's Boyle's law, which we talked about a long time ago. Therefore, at thermal equilibrium, we know that the pressure of liquid 1 times the volume of liquid 1 is going to equal to the pressure of liquid 2 times the volume of liquid 2. So PV, is equal to nRT, and PV is equal to 2/3 energy of translation. So the energy of translation is going to be equal to 3/2 times N times R times T. Now remember, this lowercase n is going to be equal to, the lowercase n is the number of moles, right? So the number of moles is going to be equal to the number of molecules divided by Avogadro's number. So the energy of translation, total average energy of translation, is going to be equal to the number of molecules times the average energy of translation for each atom molecule. So we get N times the average energy of translation is going to be equal to 3/2 times the number of atoms divided by Avogadro's number times the gas constant R times T. And remember, R is also equal to just some constant times Avogadro's number. K is Boltzmann constant. So the average energy of translation is going to be equal to 3/2 times KT, where K is Boltzmann's constant. So remember, if you take R and divide by Avogadro's number, that's equal to K, which is Boltzmann's constant, which has a value of 1.38 times 10 to the negative 23rd joules per Kelvin. Now the average energy of translation for an atom or molecule is the average translational energy of one molecule in 3D space. Now for each degree of freedom, you get the average energy of translation is 1/2 kT. Now U is, remember, the thermodynamic internal energy. So for monatomic gas, ideal gas, U is going to be equal to energy of translation plus energy electronic. So we get 3/2 times N times R times T plus the energy from electronic energy levels. Because we're going to say that rotation and vibration, that's equal to 0, because ideal gas, it doesn't have that kind of motion. So the heat capacity at constant volume is going to be the partial derivative of internal energy with respect to temperature, holding volume constant. So if we have low to moderate temperature, like up to 3000 Kelvin, then the average energy in the electron levels is going to be constant. So we can ignore it and just say, okay, the heat capacity at constant volume is going to be 3/2 times the number of moles times the gas constant R. And the heat capacity at constant, the molar heat capacity at constant volume is just going to be 3/2 R. So we have the heat capacity, the molar heat capacity at constant pressure, minus the molar heat capacity at constant volume, and that's going to be equal to R for a monatomic gas. So we know that the heat capacity, the molar heat capacity at constant pressure is 5/2 R, and the heat capacity then would be 5/2 NR. Just multiply both sides by N. Now as far as how much energy they hold, I mean, electronic energy levels, they're big, and within those there's the vibrational energies, and then within those there are rotational energies, and within rotational there are translational. And you can have so many different translational energies that it's effectively a continuum. We'll talk about that when we get to quantum mechanics. Now here's the question, how fast are these molecules moving? Well, we know that the average energy of translation for a molecule is equal to 3/2 times Boltzmann's constant times the temperature. And that's for one molecule, doesn't matter which gas, any gas. Now, the average energy of translation is also going to be 1/2 mass times the average speed squared. Lowercase v is speed. So the average speed squared is going to be equal to 3 times Boltzmann's constant times the temperature divided by the mass of the molecule. So we're going to take the square root of both sides, like this. Oops, next page. So when you take the square root of an average squared, that's called the root mean squared. So the root mean squared speed, remember, is not the same as the average speed. So we're going to do a subscript RMS so you don't confuse it with average. So the RMS speed is going to be equal to the square root of 3 times Boltzmann's constant times the temperature divided by the mass. Now, like I said though, the RMS speed is not equal to the average speed. We have these lowercase v and there's brackets, angle brackets, to show average speed. In fact, we could say the RMS speed is actually greater than the average speed. Now remember though, we only use Boltzmann constant if we're talking about a single molecule. Now K over M, Boltzmann's constant divided by mass, is equivalent to the gas constant R divided by capital M, the molar mass. So solve for K, and we get R over Avogadro's number times the mass of a molecule. So substituting that in, we get the RMS speed is equal to the square root of 3 times the gas constant R times the temperature divided by the molar mass. And to get the units to work out, you want the molar mass in kilograms per mole. R, of course, is in joules per mole Kelvin. So the RMS speed is going to end up being in meters per second. Now remember R, we use 8.314 joules per mole per Kelvin, or showing the fundamental units, it could be 8.314 kilograms meter squared per second squared over mole Kelvin. So the molecular weight, or molar mass, of substance R, or rotation. So, okay, so molar mass is in the units. Molecular weight has no units because it's a ratio to the carbon-12 isotope. So using Mi as molar mass, molar mass is just the molecular weight times 1 grams per mole. And that's it for chapter 15, section 3.